Okay, folks, let's go ahead and get started. I want to apologize for yesterday. The video ran a little longer than I was hoping, and I know a lot of you were cramming at the end there to try to get it done. Um, what I'll try to do is I'll try to streamline this video here. We don't have to worry about all the introductory stuff. I also know yesterday when we met on Zoom, it took a little bit longer than I was hoping. Today's meeting on Zoom, I think should go a little bit faster. That way, then I will give you an opportunity to get over to the video and watch it with more time. Also, I'll try to make sure that I keep the video to about 25 minutes and not run over my time. So that gives you an opportunity and gives you some time to work out the two problems that I'll have for you at the end of the video. And again, make sure if you have any questions, just make sure you comment on Google Classroom or email me. I'll be here in front of my computer and I will go ahead and answer your questions at that time. Okay, so make sure you keep that in mind. Okay. All right, so let's go ahead and let's pick up where we left off with yesterday. We were talking about how the balanced equation gives us information that we can use to run the reaction. It gives us information about the description of these the reactants and products in the reaction itself, in terms of the quantities, in terms of numbers of atoms, in terms of numbers of molecules, moles, mass, and volume as well. So what we need to be able to do is we have to be able to take the information from a balanced equation, use that to help us understand how much of the reactants and products are involved in the reaction itself. And so what I would like you to do then is we're going to start out with number 6 in your problem set here. And so hopefully you have your paper out, so get your paper. And what I'd like you to do is take these two balanced equations, and first of all, always check to make sure that the equations are balanced. But once you've checked that, take these two equations and interpret the two equations in terms of atoms and molecules. And then from there, make sure then indicate then also number of moles, and then determine and calculate for the masses the reactants and products. Okay, so take a few minutes to get this done, and then what I'll do is we'll work these out together when you get back. Okay. Okay. Let's go ahead and let's take a look at these two reactions here. Let's go ahead and interpret them based on their atoms, their molecules, moles, and masses. Okay. All right. So for this first reaction here, let's take a look at this. We see then that there's this decomposition reaction. If we want to be able to interpret this reaction in terms of atoms and molecules, we basically just take the balanced equation and then we count atoms. And so on the very most basic level, counting atoms, we've done this already. We did this back in chapter 11. So we're going to go ahead and balance this reaction in terms of atoms, or count the atoms, keep track of the atoms here. And so with that said, then I'm just going to go ahead and total the atoms here for us instead of counting them individually. If you want to, go ahead and do that on your own. Hopefully you did that. If you notice here, then we will have a total of 14 atoms to start out with in this decomposition reaction. So we have 14 atoms to start out with, and we should find that. So if you count all these atoms, you have 4 oxygens, 1 sulfur, and 2 hydrogens. That's going to give you 4, 5, 6, 7. We've got 2 of these, so a total of 14 atoms. On this side, then we should expect also to see that we should end up with 14 atoms as well. And so on the atomic level, we see that there is a conservation of the atoms. That there's a total the atoms on the left, on the reactant side, and atoms on the right, the product side, should be the same. Okay. All right. So that's interpreting this equation in terms of atoms. As we move up a level, and remember, I'm going to put this in parentheses. When we talk about molecules, we're actually counting total particles here. And so here it just happens to be all molecular anyway. Let's go ahead and count this. Okay, so what we do then is we start out with 2 molecules. Sorry about that. H2SO4. Okay, and we end up with 2 molecules of water. We have 1 molecule of oxygen and 2 molecules of sulfur dioxide. And if you notice here, at the molecular level, there is no conservation of the molecules themselves. Okay, so we have no conservation at this level. So meaning then that the total number of molecules on the left, which we start out with 2, do not equal the total number of molecules on the right, which we end up with is 5. Okay, so conservation does not occur at the molecular level. Okay, so there it is. So from the balance equation, we can obtain information about the total number of atoms involved in this reaction. And from the balance equation, we also get the information about the total number of molecules involved in this reaction as well. So let's go ahead, moving up the level. The next, this asks us about moles of each of these atom reactants products as well. And so from the balance equation, we start out then with 2 moles of H2SO4. Okay? And so if you notice here, the balance equation gives us the number of molecules and moles directly. We see that we can just take that from the coefficients as well. Okay, so we can get those numbers directly from the balance equation, meaning then we will end up with 2 moles of water, 1 mole of oxygen, and 2 moles of sulfur dioxide. And again, if you notice here, the moles are not conserved, so there's no conservation here as well. Okay, so there's no conservation either at the molecular level or at the molar level here. But again, if you notice, the balance equation gives us the coefficients of the balance equation, gives us the quantities that we see right here. Okay. All right, so with that said then, we talked about how trying to run this reaction is not possible at the atomic level. You can't isolate 14 atoms on either on the reactant side and get that to work. Okay. Also, we can't run this reaction at the molecular level either. It's impossible to isolate 2 individual molecules of H2SO4 and then from there capture 2 individual molecules of water, 1 molecule of oxygen, and 2 molecules of sulfur dioxide. It's not possible to run at that level. So what we do then is we had to scale it up to a macro level here. And so at the molar level, we have now many more molecules of H2SO4 and many more molecules of water, oxygen, and sulfur dioxide. The problem with this then is that we, as like I pointed out to you, we don't have any instruments that can measure moles of any compound. So what we have to do then is we have to convert these moles into masses. And in order to do that, it's a simple moles to mass conversion. Okay, so let's go ahead and work that one out. Okay. So first then is we're going to go ahead and convert the moles of sulfuric acid. So we start out with 2 moles of H2SO4, and we want to find then the mass of H2SO4 that we have to start out with. Okay. And so then we plug in here the molar mass of H2SO4, okay, which gives us then is going to be 98 grams H2SO4 for every 1 mole of H2SO4. And from that, then we should end up with 196 grams. So the idea then is if we start out 196 grams of H2SO4, heat it up, okay, and get it to decompose, we should end up with these quantities here. But again, we can't measure out moles. And so what do? We're going to go ahead and convert those into grams as well. So if we start out with 2 moles, if we end up with 2 moles of water, from the simple calculation here, we should be able to determine then the mass of water that we should end up with at the end of this reaction. And so the molar mass of water is going to be 18 grams per mole of water. Okay. And so with that said, then we should end up with 36 grams of water. Okay. We'll do the same thing for oxygen. We end up with 1 mole of oxygen. We can then calculate then for the mass of oxygen that we should end up with. And again, multiply by the molar mass, which is going to be 32 grams per mole of oxygen. And so therefore we end up with 32 grams of oxygen as well. So again, if 196 grams of H2SO4 decomposes, okay, we should end up with 32 grams of water, 36 grams of water, 32 grams of oxygen. And let me go ahead and erase this here to do the last part for you. Okay. So please make sure you have this written down. Okay. And so continue on then the mass with masses. With the last one, we had 2 moles of sulfur dioxide. Okay. And we want to find the mass of that. We end up with, we'll multiply that by the molar mass of sulfur dioxide. We should end up with here 128 grams of sulfur dioxide. What you should notice then is if you add up all the masses on the product side, if you add up the masses of the sulfur dioxide, the oxygen, and the water that's produced, that should equal the starting mass that you started out with, 196 grams of H2SO4. Okay, so I'm gonna leave that up to you to check that on your own. Okay, let's continue on then. Let me go ahead and do these for you. I'll leave it up to you to count the atoms here. I think you should be able to do that. But essentially, 2 atoms of aluminum. We're gonna have a total 21 atoms here of the sulfuric acid. This for a total of 23 atoms. We should end up with 23 atoms on the left-hand side. So please make sure you do that count. So we should end up, we should have 23 atoms on the left. We should end up with 23 atoms on the right, okay? In terms of molecules then, okay? We start out with 2 particles, so 2 molecules, and I'll write this again in quotes because obviously aluminum is not a molecule, but 2 molecules of aluminum. We start out with 2 aluminums and 3 molecules of H2SO4 to yield then 3 molecules of hydrogen and 1 molecule of aluminum sulfate. Okay, so that's at the molecular level. At the molar level, counting moles, we'll have then 2 moles of aluminum, 3 moles of H2 sulfuric acid. Okay, to produce 3 moles of hydrogen and 1 mole of aluminum sulfate. Okay, all right. So let's from here then, let's go ahead and get the masses together. Okay, so I'm going to go ahead. Okay, let me just go ahead and give you. We're kind of running low on time. I have it here. So I'm going to ask you to go ahead and do this here. So make sure then that you confirm this, okay, and just write this down. So 54 grams of aluminum at the end of the process. We're going to have, if you do the conversion, 294 grams of sulfuric acid. If you start out with those 2 masses, you'll end up with 6 grams of hydrogen and 342 grams of aluminum sulfate. And if you notice here, the masses should balance out. If you add those 2 up, that should give you a total of 348 grams. If you add these 2 up as well, you should end up with 348 grams, which means then mass is conserved. Okay? So please make sure then that you're able to get these numbers here. I kind of already showed you again. You're going to multiply these moles here by the molar masses, their molar masses, to get these mass values here. Good. All right. So if you have questions on how, if you're not quite sure how to get those numbers for the masses, please make sure you comment in Google Classroom or show up this afternoon at 3:15 on our Zoom class and take advantage of the tutorials, and I'll work those out for you. Okay. All right. Very good. And so the idea then here is that we should be able to determine the masses, and like I pointed out to you, the masses are always going to be conserved. Atoms will be conserved, but then if you saw what we did, the number of molecules, formula units, it simply means then the particles that are ionic in nature, the ionic compounds here. So the formula units then, remember, indicate the ionic compounds. Okay, so these are the ionic compounds. So therefore, basically, saying then that at the molecular or at the compound level, we're going to see that we won't have equal numbers on both sides. Same thing holds true for moles and volume as well. We saw that on the previous example from yesterday. Okay. All right. So let's real quick here. A couple more problems here that I'd like us to do to just kind of finish out here. So we have this problem here. We're going to interpret this in terms of representative particles. Again, representative particles we use them to describe all the particles as well. So let's go ahead and interpret this here on that level. We're going to have then two particles of dihydrogen sulfide, okay, gas. We'll start out with three particles of oxygen gas, and from that then we will produce two particles of sulfur dioxide, okay, and two particles of water. Okay, so that's interpreting this in terms of particles. Okay. In terms of masses then, let's real quick, let's do this. And I'm sorry, moles. I'm sorry, we got moles as well. So 2 moles of dihydrogen sulfide, 3 moles of oxygen to start out with to produce then 2 moles of sulfur dioxide and 3 moles of water. And again, these numbers are taken directly from the balanced equation itself. Okay. All right, so let's go ahead and solve for the masses then. So let's start out with 2 moles, and I'll do a couple of these for you. If we have 2 moles of dihydrogen sulfide, okay, to find the mass then of dihydrogen sulfide, okay, we'll multiply by the molar mass of dihydrogen sulfide, which I have here as 34 grams per mole. Okay, which gives us here then 68 grams of dihydrogen sulfide. I'm going to ask you to do, go ahead and do the rest for calculate for the masses of the remaining. So for oxygen and the 2 products that go ahead and calculate for, but I'll go ahead and give you the numbers. We'll end up with 96 grams. With 96 grams of oxygen. Okay. We will end up then with 128 grams of sulfur dioxide, and I have here 36 grams of water. And if you notice again, if you add up these masses here, they should be the same. So roughly 164 grams on the left, on the reactant side, 164 grams on the product side. So notice then that the masses are equal, but if you notice it again, masses are conserved, but there's no conservation here. These are not conserved. Okay, all right. Let's go ahead then, and I'm going to ask you to do number 15. Take about a minute or so to get number 15 done here, and let's work it out once you get back. Okay. Okay. Let's take a look at number 15 in your problem set here. So they give us the description of a reaction here. Hopefully you're able to recognize the description then as the combination, the formation of water from its elements, so hydrogen and oxygen, to produce then water vapors. So we have that. Okay. Make sure you balance out the equation. 2, 1, 2. We'll balance out the equation first. From here then we can go ahead and calculate for the molecules and the moles. So again, at the molecular level, they don't ask us molecules, to count the atoms. So we start out with 2 molecules of hydrogen and 1 molecule of oxygen to produce then 2 molecules of water. Okay. At the molar level, okay, we have then 2 moles of hydrogen reacting with 1 mole of oxygen, and that will produce for us 2 moles of water. Again, so these we just take straight from the balanced equation. Okay. All right, so let's go ahead then, and they ask us to find the volume of these gases, and these gases are at STP, so we can go ahead and use the molar volume. So let's go ahead and calculate for the volume of these gases involved in the reaction, and let's go ahead and work this out. Okay, so if we start out with 2 moles of hydrogen, okay, and we want to find the volume, and remember the volume you will get will be in liters because the molar volume is in units of liters per mole. Hopefully you recognize then why we will have to multiply by the molar volume in order to get our answer. Okay. And so if you multiply that in, you're going to get then 44.8 liters of water. Doing the same thing with oxygen, 1 mole of oxygen. Okay, we're going to find the volume of oxygen that we need to start out with. We'll multiply again by the molar volume, which is 22.4 liters, this time of oxygen, for every 1 mole of oxygen. We end up then with 22.4 liters of oxygen. So we need to, if we start out with 44.8 liters of, I'm sorry, hydrogen here, not oxygen, hydrogen. Sorry. If we start out with 44.8 liters of hydrogen and 22.4 liters of oxygen, we will end up with then, if we calculate for this, okay, we can calculate for the volume of water that we form, because this is water vapors. Okay, we will again multiply that by the molar volume. Okay, we'll end up with 44.8 liters of water. And so if you notice here, volume is also not conserved in this process. Okay, so only mass and only volume atoms are conserved in this process. Okay, all right, very good. So make sure you write that down and work that out. Okay, I'm going to ask you to do one more problem here, and we'll finish up with the this interpretation of chemical equations. Okay, so go ahead and take a look at number 16, work that one out, and then I'll provide the solution for you, and then we'll continue on. Okay, so go ahead and work that out. Okay, so let's go ahead and interpret this equation then. They want us to compare masses of reactants, so they want us to get masses here only. Okay, so we don't have to do anything else. Let's go ahead and calculate for the masses. Start out with it, make sure you get the balanced equation. If you notice here, the equation is not balanced, so make sure you write down the balanced equation, folks. You always have to have that first. So the coefficients here to balance the equation, it's going to be 4, 6, 5, 6. Okay, so 4, 6, 5, 6 will help us balance out the equation, which means then, and here they want us to solve for masses of reactants and products. Find the mass of ammonia to start out with, and we have to recognize then that we have 4 moles of ammonia that we start out with. Okay, so we have 4 moles of ammonia. To get the mass of ammonia in grams, we're going to multiply by the molar mass of ammonia here, which is going to be then 17 grams per mole. Okay, so make sure you're able to do this calculation, because what we'll do next will involve this calculation, okay, which gives us then 68 grams. Okay, so we have then 68 grams of ammonia that we're going to start out with from this balanced equation. For the nitrogen monoxide, then we know that we have 6 moles of nitrogen monoxide we will start out with from the balanced equation. We're going to go ahead then and we'll calculate for the mass here. We'll in grams of nitrogen monoxide. Okay. And so the molar mass of nitrogen monoxide is going to be 30 grams of NO for every 1 mole of NO. And so therefore, if you work that out, it's going to be 180 grams of nitrogen monoxide. So again, what we would get from the balanced equation here is that we need to start out with 68 grams of ammonia and 180 grams of nitrogen monoxide. If we do that, we should form then, based on the balanced equation and what we have here, okay, this amount of nitrogen. So let's go ahead and plug that in. We have then 28 grams per mole. Okay, and we should end up with then 140 grams of nitrogen. Okay. And finally, for the water then, with 6 moles of water. Okay. To find the mass of water that forms, we'll multiply the moles by the molar mass of water, which is going to be 18 grams per mole. Okay, and so we end up here with 100 and 8 grams of water. Okay, and if you notice here, if you add up these two masses here, you should end up with 248 grams total. Yeah, these two masses here, you should end up with a total of 248 grams as well, because mass is conserved. Okay. All right. So hopefully you get this. Please make sure, again, if you aren't quite sure how we do these conversions, you contact me. You send your questions to me, and I will, or meet me after on our Zoom classroom after school today and ask your questions. Okay. And if you notice here, all these compounds are gases as well. So if this reaction was run at STP, we should be able to calculate the volume for this. And so just as an extra practice for you, if this reaction is run at STP, I'll give you the answers here and make sure you are able to get this. We should end up with then, you start out with 89.6 liters of ammonia, 134.4 liters of nitrogen monoxide. And if you mix those two together, you should end up with 112 liters of nitrogen and 134.4 liters of water. Okay, so please make sure you can get these values here. And again, that's only if this reaction is run at STP. The problem did not specify that, so again, you wouldn't be able to work this out. But if the problem had specified STP, make sure then that you are you can work out the calculation to get these numbers here. Okay. All right, very good. Let's continue on then. And I want to go ahead and finish up today by talking about how we can do these calculations. Use these calculations here to determine quantities of reactant product that goes into a chemical reaction. Okay, so what we're going to do then is we're going to be able to determine then amounts of reactants and products that go into a particular reaction. And to do that then, I need to introduce to you a new conversion factor that involves these moles, okay, and it's called the mole ratio. If you look at a balanced equation, what you're going to notice then is that, again, we saw this, the balanced equation gives us information about moles. What that balanced equation tells us then that is that there is a relationship between these mole values here, which we're going to take advantage of. And when you compare the mole values, you can set up a ratio, and that ratio is what we call a mole ratio. So the coefficients then, if we set them up and we compare them, we will get this mole ratio, and that mole ratio then will allow us to do the conversions that we need to do involving the amounts of reactants and products. Okay? And so this mole ratio is simply a ratio, you guys, between the moles of reactants, the moles of products, the moles of reactants to products. And so we can use that to do our conversions between any of the components of the reaction. Okay? And so it's basically a conversion factor that we should be able to take advantage of. Because what this mole ratio tells us, and let's take a look at this here, what this mole ratio tells us is the amounts of reactants. It compares basically the amounts of reactants to reactants to product. It compares the parts, the component parts of the reaction itself. Okay? So for example, in this particular problem here, remember we did this already. From the balanced equation, we're told then that we have 1 mole of nitrogen to start out with and 3 moles of hydrogen to start out with. And when we mix those two together, we will get 2 moles of ammonia. Okay. All right. What this equation also tells us is then if you mix 1 mole, if you mix exactly 1 mole of nitrogen with 3 moles of hydrogen, you will produce 2 moles, exactly 2 moles of ammonia. What we are saying here is that these are all equivalent. They are all equal to one another. So let me repeat that. What this equation is telling us then is that if we start out with 1 mole of nitrogen, we mix it with exactly 3 moles of hydrogen, we will get exactly 2 moles of ammonia. Okay? And so you notice that if these are equal, we can set up these ratios. Okay? If these two are equal, let's focus on these two here. We can set up the mole ratio between nitrogen and ammonia because they're equal. So the first mole ratio then is going to be the moles of nitrogen to the moles of hydrogen. So there is 1 mole ratio that we can obtain from this balanced equation. Then we can see this equality here. we have then 3 moles of hydrogen and 2 moles of ammonia. Okay, so that's the second mole ratio that we can set up from this equality. And finally, if these two are equal, then the amounts of the moles of nitrogen has to be equal to the amount moles of ammonia. So we can set up our third mole ratio from that relationship, which is going to be then 1 mole of nitrogen, 2 moles of ammonia. Okay. All right. So let's go ahead then. I'm running a little low on time. And so what I'd like you to do then is take this problem here. Okay. And okay, so I'm running low on time. What we'll do then is tomorrow we'll pick up with this problem here, and we will calculate the mole ratios that we can derive from this particular reaction. From there, we'll use the mole ratio in order to do their calculations involving masses, okay, because that's what we want to be able to do. All right, so I'm going to stop right there. We'll pick up with this problem tomorrow. We'll start with a review of mole ratios tomorrow as well. And then you'll be able to get your work done. We'll be able to continue on the discussion of the stoichiometry tomorrow. Okay. All right, folks. Again, hopefully, if you have any questions, let me know. And hopefully I'll see a few of you this afternoon on our Zoom classroom. Okay. I'll see you tomorrow then.